Hello everyone. In this video we are going to talk about the degrees of freedom of more than one rigid body, because we know a rigid body in the space has 6 degrees of freedom. And if you constrain it to only move on a plane, then it's going to go down to 3 degrees of freedom, which, by the way, we call it a planar constraint, and we're going to talk about it. But now, when you have more than one rigid body, when you combine them into a mechanism, a robot, a structure, anything like that, now what is the degree of freedom for the entire system? Okay, that's what we also call mobility. And the method to determine that is typically called Grblers Formula. The more complete name of it is the name of the 3 people, ChebyChev-Grübler and Kutzbach criterion. Okay, we might also call it mobility criterion, but most of the people know it with the name of this scientist Grubler, and it is quite simple. It says, well, let's say if I have n rigid bodies, okay, and one of these n rigid bodies in my system is grounded. It is connected to the ground by any method, which we might also call that a rigid joint or a rigid constraint. Like we have welded it down to the ground, we have bolted it, we have used any method of rigid connection so it does not translate and rotate. So the degree of freedom for that is 0. So if you have n rigid bodies in your system, with one of them being the ground member, correct? Let me reduce the size here. So, right, you have n rigid bodies, one of them is the ground, then the total degree of freedom for all of these n members is n minus 1 times 6. Why again minus 1? Because one of them is the ground link. So this is the overall degree of freedom, DOF, of the system if there is no constraint. Now, in most of the systems, there are always constraints, right? You connect these rigid bodies somehow. It's not like each one of them can completely act freely, right? For example, let's say here I have 2 objects, and then out of these 2 objects, in order to connect them, I might what? I might apply a hinge or a pivot, correct? Like this. Then now what's the degree of freedom? Okay. Or let's say, for example, here I have the other type of constraint, we call it prismatic. Or we have the screw joint, or we have the universal joint, or cylindrical joint, spherical joint, planar constraint. We have the we call edge surface contact. We have the point surface contact, and so on and so forth, right? So when we have these types of constraints, then how would they affect or reduce from these degrees of freedom? So it says, if you have, let's say, m constraints or k constraints, and each one of them has so many reductions in degrees of freedom, correct? If you show them by f, for example, small f, so f sub I means what? Means the degree of freedom that the ith constraint is taken away from the total system. So if you sum all of these, correct, over I, and let's say I goes from 1 to whatever you want, k, let's say you have k constraints in the system. If you subtract all this from these total available degrees of freedom, that is your overall degree of freedom for the system, or we call it the mobility of the system. Okay, we also have that name for it. Okay, so this n again is the number of rigid, but it's not a big deal. The thing is, now what is the, let me write it down. So this is the number of rigid bodies, including ground. Okay, So now the question is, what's the degree of freedom that each one of these types of constraint is taken away? So if you have this, as I said, we call it the pivot. So this pivot or hinge, you might call it, what this hinge does, if the problem is 3D in general, it takes away 5 degrees of freedom. Why? Because if you fix one of them, the other one that is pivoted, let's say this link here is attached to the ground, and this one can rotate about the pivot, all it can do is one single rotation, and that rotation is definitely about this axis. That's all it can do. So it can only what? Rotate. Let me show it this way maybe. It can only do a simple rotation about that axis. That's it. So it takes away 5 degrees of freedom. If you have this prismatic joint or constraint, then again, all it can do is one single translation along the direction of the groove, and that's all it is, or the guide. It cannot do any other translation or no rotation at all. So again, for this one, the degree of freedom it takes away is 5, and it only leaves you with 1. Okay, if you have the screw, so one object is like the nut, the other one is like a bolt or screw, and you know, when you bolt something or put the bolt in the nut and turn, let's say if this guy is here fixed, then the bolt can go forward and backward, and it can also spin about its longitudinal axis. And that's quite similar to this one, which we call the cylindrical joint. Okay, so this is the cylindrical joint. This is called the screw joint. And the thing is, they look very similar because in the cylindrical joint also, if one object is fixed, the other one can go backward, forward, and it can also spin about its axis. So what's the difference between these two? The difference is this. When we say degrees of freedom, these degrees of freedom for the entire system, they have to be independent motions. If they do depend on each other, then we do not count all of them as degrees of freedom. Only we count the independent ones. In the case of the cylindrical, this longitudinal or translation motion is independent from the rotation. So here, actually, the degrees of freedom this guy takes away is 4, and it leaves you with 2 degrees of freedom. But here, the advance in this axis is related to the amount of rotation. And the reason is because here there are threads on both objects that are engaged, and they do not allow the free advance, right? So if you want to move the bolt in the nut in this direction along this axis, you cannot just freely move it. You have to keep rotating so it moves backward and forward. So basically, if you rotate this bolt, let's say by 2 pi radians here, correct? Then the amount of advance is what we call P, or pitch, right? That's the pitch of the thread, which is the distance between one thread to the next. That's all it can go forward and backward. So you see, one motion does depend on the other one. They are linearly related. Therefore, this guy does not leave you with 2 degrees of freedom. Only one of them is independent. The other one depends on the other one. And one of them depends on the other one. And so the degrees of freedom this guy takes away is actually 5. So it looks like cylindrical, but it acts similar to actually hinge or prismatic, not the cylindrical. Okay. So the other one we have that leaves you with 2 degrees of freedom is universal joint, or U joint. Okay. And universal joint, if you know, it is used in transmissions of rotary motion from one axis to the other when the axes are at angle. and they are not parallel, not perpendicular most of the times, and most of the times also not or always not skew axis. So they are at angle intersecting, like let's say 45 degrees, or maybe you call it 135 degrees. So here you have 2 degrees of freedom, okay? And that's because here you have 2 objects pivoted using what we call this cross member. Okay, so we have the 2 yokes and the cross member, and here you can have a rotation about this axis, and then you can have a rotation about this axis. So this one also takes away 4 degrees of freedom and leave you with 2. Then we have spherical joints, which is allowing you to have all 3 types of rotations but no translation. Okay, so here you can have all sorts of rotation, and it might not be super easy for me to show it, but one of them is this spin here. The other one is if you consider this axis, then it is going to be like that rotation. And if you consider like this axis, then the other one is going to be like that. Okay, so this one leaves you with 3 degrees of freedom, and it will take away 3 degrees of freedom. Okay, and this is what you see in your shoulder, in your hips, and to some extent in your wrist. Your wrist is really does not allow for too much of spin. It's quite like I would say something like that. Okay, so we have 2 rotations. So wrist is not like a perfectly spherical joint. Your shoulder is better, your hip is better, your wrist kind of, but it has limitations. Although those other ones also have limitations, you cannot do full rotations along all 3 axes. So that's the spherical joint, and then we also have the planar constraint. So as I said, any object that is limited to be on a plane. So let's say here this plane is fixed, and this object has to keep its contact with that plane. So all it can do is one translation along this axis, the other perpendicular to that, and then a rotation on the axis perpendicular to the plane. So this planar constraint also leaves you with 3 degrees of freedom and takes away 3 out of 6. Then we have edge on surface contact. So here there is this edge down below. If you can draw this thing a little bit better maybe. Then there is this edge at the bottom, this one. And this edge is going to keep its contact with the bottom surface all the times. And because of that, what you can do is actually a rotation about the axis perpendicular to the plane, this rotation. You can move along this axis, you can move along this axis. You cannot go up because the edge contact with the surface is going to go away. You can have this rotation, right? So the object can tilt forward, backward. You cannot have this rotation because if you do, then one side of the edge is going to get off the surface, okay? So this rotation and this translation are off. They are out of the possibilities. So you have 4 degrees of freedom left and 2 of them are gone. So Fi for this guy is 2. And then you also have a point on surface contact. Where all you need is basically a point. Like if you have a spherical surface, a point has to only be in contact with the surface, and now all you cannot do is to move this whole surface in the upward direction. So this translation is out of the way, but you can do all of the rotations, and you can do these two unplane translations. So this one only takes away 1 degree of freedom and leaves you with 5. Okay, so these are different types of constraints with their names, and I showed you the Fi, or the degrees of freedom each one is taking. If you take that summation out of the total degrees of freedom available, then you have the total degree of freedom left for the system. And well, let's take a look. Okay, let's take a look at some of the cases. Now, again, if your system is planar, so this is for 3D problems. Okay, so these are 3D problems. If the problem becomes 2D, which is planar, then here, this guy, instead of 6, it becomes 3, because each object only has 3 degrees of freedom, right? You're applying basically this constraint to each and every one of them. So let's look at some problems together and practice this. So one case is going to be here. 2 gears I have, and they are both pivoted here and here. So I have a pivot here, and I have another pivot here. Okay, and there is this contact point here. So what's the degree of freedom here? So this problem is 2D problem, okay? And so the degree of freedom is going to be 3 times n minus 1. Now here, if you don't count the ground here, which can be one of these pins, then all you have here, that n minus 1, or the number of moving objects for you in this case, is 2. So there's going to be 3 times 2, right? 6 degrees of freedom total. Now minus, so here you have 1 pivot and 1 pivot. And what's the degree of freedom that the pivot takes? Well, if we go back, the pivot should take away what? 5 degrees of freedom. But when the problem is what? 3D. When the problem is 2D, 3 out of those 6 motions are not available at all. So all it can take away from you are the 2 translations. These guys are out of the way. You're only down to 1 rotation. So in 2D cases, the Fi that a pivot would take away is 2. And the similar thing for prismatic. This is also 2. Okay, so these ones that I'm writing in red, these are for 2D cases. The ones in black are for 3D cases. And as I said, the degree of freedom that you will have for the case of 2D problems, it is going to be 3 times n minus 1. And then minus summation Fi. Some people also write this for 2D cases. They write this as 2 times F minus C. Okay, where F here is those constraints that take away 2 degrees of freedom out of this any rigid body, and we call them the low pairs. So just wanted to tell you these terms. So this is called the number of low pairs, or surface to surface contacts. Like what? Like a pivot or a prismatic joint. Okay, these are low pairs, and there is surface to surface contact. Clearly, you see here that the 2 objects have surface to surface contact. C is what we call the number of high pairs, or the ones that take away 1 degree of freedom only. And these are what? These are like basically edge contacts or point contacts. So let me call this surface contact, not surface to surface, although you can call it, that's okay. And as I said, here you might call it edge or point contacts. Okay, and that's like what? That's like this case here. This contact that you see here, this is basically in 2D case, it is going to be an edge or a point, really. In 3D, it's an edge. In 2D, it is like a contact point. So here, you have 2 low pairs and you have 1 high pair. So this is going to be minus 2 times the number of what? Low pairs, which is 2, then minus 1 times the number of what? The high pairs, which also it is 1, correct? And so clearly, again, you see that C, the number of high pairs is 1, and then the number of low pairs are these 2 pivots, which is 2. And so the degree of freedom, if you look at it, calculated 6 minus 4 minus 1, that is going to be 1. So it says that the degree of freedom for 2 gears that are meshed together and they are both pivoted down to the ground is 1. And what does that 1 mean now? It means that although each one of these is rotating, correct? Each one has a rotation and an angle, but these 2 angles are not both independent parameters. Once you know one of them, you can find the other one. Okay, only one independent parameter in the system exists. So for example, if the RPM or angular velocity of this gear is omega 1 and for this one is omega 2, and then the radii are R1 and R2, then you can show that omega 1 over omega 2 is equal to R2 over R1. Which basically means the gear that is larger is going to rotate what? Slower, and the gear that is smaller is going to rotate faster. What is this R? We'll talk about it later in machine design videos, but this is called the radius of the pitch circle in a gear, and it's not really from the center all the way to the crest of the tooth, or what we call the addendum radius. So, again, once I know one of them, right? So if I know omega 1, let's say, since this ratio is constant, and I know it, then I can definitely find what? Omega 2. So omega 2 is not also independently controlled. It is controlled by omega 1. Okay, so that's the meaning. Now, let's look at another example here. Let's say we have a cam and follower mechanism. So this is your cam, this object, and this object that goes up and down, this is the follower. And the follower is limited to move inside this bearing, so all it can do is go up and down. And this cam is pivoted down, so all it can do is to rotate. Okay, so as this guy is rotating, this guy is going what? Up and down, and this is what you see in your cars. This is the valve that opens and closes to let the mixture of air and fuel get inside the combustion chamber of the engine, and then when it closes, explosion happens. Energy is transferred to the crankshaft, and then the burned mixture of air and fuel is going to get out of the cylinder once this valve or the follower goes up. And this cam here is mounted on a shaft. We call it the camshaft. and the camshaft is driven also by the crankshaft. So this is the mechanism for opening and closing the valves inside the engine. And now if you look at the degrees of freedom, again, I have two members that can move. So if you want, you can call this back block the engine block. You can call it the ground, fine. But all you need is the number of moving objects, which in this case is 2. Now you see here I have one low pair, which is a pivot, and I have another low pair, a prismatic joint. And so the number of low pairs for me is 2. And then here in the middle, I also have again a point contact. And so the number of high pairs for me is equal to 1. So just like the previous case, the degree of freedom is going to be 3 times 2 minus 2 times 2 minus 1 times 1. And again, it is going to be 1. And again, it means that if I know the rotation of the cam, then I can determine the translation of the follower. Okay, or if I know the RPM of that, then I can find the linear velocity of the follower at any point. Okay, so let's look at some more examples. Another one is the 4-bar linkage. So here you have 4 members. One of them is called the frame or the ground here. Definitely you have this member fixed, the gray one. Then you have the green member as your input. We call it the crank. You have the coupler mechanism, link, sorry, and you have the rocker, or it could also be a crank. So what is crank? What is rocker? Crank means that member is going to go full revolution. Okay, if you go full revolution in that member, we call it a crank. If it only goes between 2 angles and oscillates back and forth, we call it the rocker. So the 4-bar linkage can be a crank, it can be a crank rocker, and so on, depending on the length of these 4 members. Okay, you have all forms of configurations of the 4-bar linkage. There are some inequalities which will tell you what kind of motion you will get. You might even have a a rocker, so your input member can also oscillate. And this is used a lot in so many different places, like into trains to transfer the motion from the first wagon to the rest of them, or inside your steering mechanism, the Ackerman mechanism to steer your tires when you turn the steering wheel is also this guy called the Ackerman trapezium, which is a 4-bar linkage, and you'll see this guy a lot, and we'll talk about it in future videos. But this frame member is pivoted down, and then the crank is pivoted to coupler and rocker is pivoted to coupler. So I have 4 pivots. I have 4 members, but one of them is the ground. So in this case, n is 4, but remember, one of them is the ground, so you have to subtract it. And all I have is 4 low pairs of pins. There is no contact. And the problem is clearly a 2D problem. So each object only has 3 degrees of freedom. So my total degree of freedom in this case is going to be 3 times 4 minus 1 because one of them is the ground, minus 2 times 4, and there is 1 times 0, and it's 9 minus 8, and then again it is going to be 1. And 1 means, again, what? It means if I know the angle of, or omega, or RPM of the input link, then I can definitely determine analytically the RPM of the output link, as well as the RPM and the translation of what? The coupler link. Okay, so all I need is this one. Once I know this one, then everything else is going to be determined based on the geometry of this guy. More examples. Another one, slider crank mechanism. This is exactly your engine mechanism. So here this member is the crankshaft, this is the conrod, and this is the piston, which is moving inside the cylinder. Again, if you count the cylinder, the number of rigid bodies you have is the cylinder or the engine block, that's 1, the piston 2, conrod 3, and crankshaft 4. So you can say N is 4, with considering that one of them is, again, this member that is, all of these gray guys are all fixed. And the number of low pairs, the one that take away 2 degrees of freedom, are, you have 1 pivot here, you have 1 pivot here, you have 1 pivot here, that's 3, and then you have the prismatic joint here. Okay, there is no contact other than this prismatic, which takes away 2. So if you look at your degrees of freedom, again, very similar to the 4-bar linkage, it is going to be 3 times 4 minus 1 minus 2 times 4 and minus 1 times 0. So then again, it's going to be 1. And again, 1 means if I know, let's say, the motion of the piston, if I know how piston is going back and forth, depending on which one input, which one output. Let's say in the engine, the input is coming from piston and the output is in the crankshaft. So if I know the linear velocity of the piston, then I can determine the angular velocity of what? The crankshaft, as well as the motion of the total motion of the conrod. I can determine everything analytically. Okay, so that's called the slider crank mechanism. Let me, by the way, write them down. I'm not sure if I have the names here, because these are important and I want you to know the names. So this is called the 4-bar linkage or 4-bar mechanism. This is called the slider crank. Mechanism. This is called the cam and follower. These are, of course, meshed gears or a gear train. And the next one that I want to talk about is what we call planetary gears. Let's see if I can write it down here bigger. Planetary gear train. And this is what you will see if you look at the automatic transmissions in your car. In manual transmissions, you have gear pairs like this, several of them on several shafts. In automatic transmissions, you have 2 or 3 planetary gear set like this, and some other components. Now, what's the degree of freedom for this whole thing? So here you have, let's count the number of moving members. So you have the center gear, which, by the way, we call it the sun gear. We have this outer internal gear, which we call the ring gear. If you look, this is an internal gear. The teeth are inside. We have typically 3 gears between the sun and the ring, and we call them planet gears. And then we have this red member, which we call the planet arm. Okay, and it's attached to the axis of all 3 planet gears. So we have 4 members that can move. So here your n minus 1 is equal to 4. You have 4 moving members. And now, what are the constraints? So if you look here, now it's not really 4, because if you count all of the planet gears, you really have 6 members that are moving. But here, for the simplicity of analysis, I only consider one of the sun gears. So I'm not going to count all 3 of them. I only consider one of them. The degree of freedom is not going to change by adding more of these planet gears. And you can check it at home if you want. But here, for the simplicity, I'm going to use what? So let me only counting one planet gear. Oh, no, I need to write it. So only counting one planet gear. Okay, so now what are the constraints? Well, the constraint I have is the ring here, and this is a 2D problem. This is a 2D problem, and I do not need to consider it like a 3D problem. I can completely treat it like a 2D problem. Let me see if I can get some of this stuff out of the way. Oh, no. Fine, let it be here. So what I have a pivot here, so the ring shaft is pivoted to the ground. This is a darker color. So I have a pivot here, because this shaft is pivoted to the ground. I have one here. The shaft of the planet arm is also pivoted to the ground. Then I have another pivot here. The shaft of the sun is passing through the middle of the shaft of the ring or the planet arm, and it is also pinned down to the ground. So this guy has again an axis, a shaft that is typically inside the shaft of one of these guys, and then I have a pivot here, right? So each one of these planet gears is pivoted to the arm. So I have 4 pivots, and then I have 2 contact points, one here between planet and the sun, one here between planet and the ring. Okay, so the number of your low pairs is equal to 4 pivots, and the number of high pairs or contacts is 2. So the total degree of freedom, if you calculate it for a planetary gear train, it is going to be 3 times 4. We don't need to subtract 1, it's just 4 moving members, minus 2 times 4 and minus 1 times 2, and it is going to be 2. So a planetary gear train has 2 degrees of freedom, not 1. And what does that mean when you have more than 1 degree of freedom? Now what does that mean? It means, for example, if I want to know the RPM of this arm, okay, the planet arm, if I need to know that, instead of having one other motion fixed or determined, I need to have 2 of them fixed. Like what? Like, for example, if I want to know the omega of the arm, correct? If I want to know what is this guy, I need to know omega of the ring and omega of the sun. Actually, this is omega of the sun, this is omega of the ring. I need to know 2 inputs to have 1 output. For example, I might fix the ring and turn the sun and then so I have 2 inputs, one of them 0, one of them non-zero, and then take my output from the arm. Or I might I might fix the sun, turn the ring, and get my output from the arm. Or I can do the other way. I can move the arm, fix the sun, get my output from the ring, or move the arm, fix the ring, get my output from the sun, and so on and so forth, right? So there are 3 major members, the planet arm, the ring, and the sun, and I can move or determine the motion of 2 of them, get the output from the other one, and it means it gives you 6 different types of motion, 6 different combination of input output. Okay, let me write it down here. So you have 6 different combinations of inputs, because you have 2 of them, and output, because you have 1 output. And that's what makes this guy be used in transmissions, because this guy alone by itself can give you different, what we call speed ratios. What is a speed ratio? If we go back here, you see the omega of the input, if 1 here is the input, over omega of output is equal to a fixed number. This ratio, if we call 1 to be the input and 2 to be the output, this guy is what we call the speed ratio of this gear set or gear train. Okay, or SR, speed ratio. So, and that's the most important thing in a gear train, a gearbox, the speed ratio. When you put your car and you're driving a manual car and you put your car transmission in low gear or high gear, all you're doing is you're changing these input output sets and you're changing this ratio R2 to R1, and so you're getting different speed ratios. So if the input is coming from the engine, then the output that goes to your tires, your wheels, will be different for different types of gears. Low gears will give you a smaller output, so the car goes slower, but you get more torque. High gears, they make the output turn faster, so your car goes faster, but you're gonna get a smaller amount of torque. Please watch my videos on dynamics of rigid bodies, rotations, and I have explained more about this speed ratio and so on. So clearly you see this planetary gear will give you 6 different combination of input outputs, or 6 what? Speed ratios. There are other things that have more than 1 degree of freedom, and that includes your robotic manipulators, right? Your robotic arms or manipulators, they all have typically more than 1 degree of freedom, right? For example, here, this is what we call the 3 degree of freedom planar arm. So if you ever hear that, this is called the 3DOF planar arm. So everything is planar, everything is 2D, but you have 3 joints that you can actuate. So you have joint 1 here, joint 2, and joint 3 with angles theta 1, theta 2, and theta 3 under your control. Clearly here you have 3 members that you can move. So n minus 1 is 3. And then you have 3 pivots, 1, 2, and 3, and that's it. You have 3 lower pairs, no higher pair, nothing. So the total degree of freedom for this guy is going to be 3 times 3 minus 2 times 3. That is going to be 3. And of course it is 3 because you can independently actuate theta 1, theta 2, or theta 3, or all 3 of them at the same time. So if I want to know the speed of any point, the motion, the position of any point, let's say the most important point of the robot, this point, which as you know in robotics we call this guy what? The end effector. If I want to know how fast the end effector is moving, correct, I need to know how fast each one of these 3 joints is rotating. So I need 3 inputs to have what? 1 output. Once I know these 3 inputs, then I can have the motion of the end effector. Okay, the speed of it, acceleration, whatever it is, the velocity components. Okay, so the more degrees of freedom your system have means you need to provide more inputs to determine everything, to know your specific outputs. Now, we talked about systems with one or more than 1 degree of freedom, but what about systems that have less than 1 degree of freedom? Like, look at this truss here, correct? So clearly this is a what? This is a planar truss. And this is what you have in bridges or so many other places under the roof of the many houses, factories to bear load. So here you have, as you can see, I have 7 members. Each one of these bars is a member. And in reality, these members are not always pivoted. In trusses, when we try to analyze them, we assume that the members are pivoted. Most of the time, that's not the case. They are actually welded here or bolted down to each other. So they are not real pivots. But in this case, if we want to make life easy and go just like what you studied in statics and say all of these guys are pivots, in reality, they are not. But if they are, then I have 5 pivots here, and I have 7 members. So n minus 1 here is 7. I'm not counting the ground. I have 7 members, and I have what? 5 pivots, right? Wrong. It's not 5 pivots. It's more than 5. Why? Well, the thing is this, that's the trick. Whenever you have more than 2 members joined together, you should not count the pivot as 1. So here, yes, the pivot is 1 because only 2 members are pivoted together. But what about here? You have 3 members pivoted together, and to make that happen, you need 2 pivots. Although they might be coaxial, but each 2 of them you connect with 1 pivot, so you need actually 2 pivots, although they might be on the top of each other. Here you have 2 pivots, you have 3 members. Here you need 1, and here you have 4, so you need 3 pivots. So if you have n members, you have n minus 1 pivots to keep them in place. So now if we count, you have what? You have 6 and then 9, correct? You have 9. Now what? Is that good? Again, let's count the members. That's 1, 2, 3, 4, 5, 6, and 7. So now what's the degree of freedom here? DOF equals, and it is going to be what? It is going to be 3 times 7 minus 2 times 9, and that is going to be giving you 3 degrees of freedom. Really? Do you think a truss can have 3 degrees of freedom? No. So what happened? Where did we make a mistake? I'll tell you. I deliberately took you, and that's what I sometimes do to my students in class. I take them with me in the wrong direction knowingly, and I want to know if anybody is objecting or thinking out of the box and saying, hey, what you are saying does not make any sense. I want that. I want my student to think for themselves and not taking everything from me just because I say so. Okay, so what did we not include? Yes, these supports, right? We did not care about these. Well, here, that's right. These 2 members are pivoted together. Fine. But how are those 2 members are attached to the ground? We have forgotten about the connection of the truss to the background, to the ground, right? The pin that is connecting these 2 guys together, it is only allowed to do a simple what? A simple rotation. Okay, so this contact point here in red cannot go left and right, and it cannot go up and down. It's not possible. It can only do a rotation. So actually there is an extra pin here because one of your members is also the ground. So if you count the ground and here count this guy as a member, so say n is 8, with the 8th member being the ground, these guys in green, the fixed ground, then here you have 3 members pivoted together, so your actual number of pivots here is 2. So this is not 9, it is actually 10. And what about here? That's right, you have a pivot, but that pivot is now added to a roller. So this contact point, it can do this rotation, and it can also move horizontally. It can the only thing it cannot do is go up and down. So here you have one contact actually. Okay, you want, I can show it like this for you. Let me draw it in a way that is nicer. So here I call this member this guy in green, I call it the ground. So what I have here is what? I have 2 connections because I have 3 members pivoted together. So I have 2 pins. So if I want, I can say this is what? This is 2 and not 3. Write it closer. And here I have 1 pivot, but I also here have a contact. So I have what? I have 1 contact here. Let me use a different color here, maybe. I have 1 contact. So now if I calculate my degree of freedom properly, it is going to be 2 times 10, and then minus 1 times 1, and guess what? You are going to get 0. So the degree of freedom here is 0. This system cannot move. The system cannot move. 0 means the system is in static position. It cannot move. Okay? But sometimes not only you can get 0, you can get less than 0. So here I have 1 member, just this beam here, from left to right, from A to B. That's all I have that can move. And so here n minus 1 is 1 simply. I only have 1 member that can move, but I have a rigid connection here on the left and a rigid connection on the right. I have 2, 1 here on the left, 1 here on the right. And each rigid connection takes away what? 3 degrees of freedom. So this rigid connection here has Fi of 3. This rigid connection also here has Fi of 3. So my degree of freedom is going to be 3 times 1 minus 3 plus 3. And you will get negative 3. Negative 3. What does negative mean? The same thing could have happened here if instead of having a roller here, you also pinned down this side. So instead of a pivot and a roller, if you made it a pivot and a pivot. So did not allow the right side to go horizontally, only a pure rotation. If you make here also on the right side a pivot, then no contact, but F was 11. And so you will have 3 times 7 minus 2 times 11, you will get negative 1. Okay, and what does negative mean? So if here, again, I made it a pivot, it was negative 1, clearly here, you see it's negative 3. Negative definitely means it is static. It doesn't move, but it tells you one more thing. When it's negative, it means the system is what? It's called over-constrained. The system is over-constrained, and in your statics, you also call it what? You are right. We call it statically. Say it. Yes. Indeterminate. Which means here I have 6 reactions and I only have 3 equilibrium equations. I cannot find all 6 of them through statics. If I want to find them, I need to go to solid mechanics and bending of the beams to find it. Okay, so if the system is over-constrained, means it's statically indeterminate and you cannot find all of the external reactions. While when the degree of freedom is 0, it's statics, but it is what? It is determinate. Means you can find all of the reactions. So here you have 2 reactions on the left, 1 on the right, and you can find all of them. Okay, so that's the meaning of 0 and negative. Anything less than 1 means the system does not move. It's a structure. It's a structure, but negative means you have applied more constraint that you needed, and sometimes it's not really good. Like in this case, one of the reasons we put the roller here is if there is no external load or anything, or even there is external load or there is thermal load or anything, this side can move a little bit left and right, and it does not add more extra stress to the beam members, to the truss members, than you should. Okay, so by allowing this motion, you're trying to reduce the amount of stress, tension, or compression in the members. Okay, because if you fix this side, then this point cannot move at all. And then if there is even no physical load, but just like thermal load, that will also cause thermal stress, which then can be added to your physical stress due to the loads, physical loads, and that will bump up the total stress in the members and break them faster. Okay, so hopefully I told you enough about the meaning of degree of freedom for a system of rigid bodies, which we call the Grblers Formula, or called ChebyChev-Grübler-Kutzbach mobility criterion. And let me call it mobility formula. Maybe this is a little bit easier to understand. Okay, and you learn about different constraints and how to work out a system of rigid bodies. Thank you so much. See you in the next lecture.